Let's keep going with chapter 6.8 part 2. Let's think about the horizontal p-test. Try to remember it from scratch, just off the top of your head. It's a good mental exercise because we're going to need it, and something we write next. So ready? Pause the video, come back. All right, so it's the integral 1 to infinity 1 over x to the p dx does what? Converges. The integral converges if or diverges if p is less than 1, greater than 1, equal to 1, what? It was converges if p is greater than 1 and diverges if p is less than or equal to 1. Remember, 1 over x squared is actually less than 1 over x, and 1 over x is kind of like the boundary between converging and diverging integrals for p test stuff. So hopefully you remembered that or could reason it out again for yourself. Let's give ourselves another problem. How about the integral 1 to infinity 1 over x cubed plus, let's throw some other numbers on here, like 29x squared plus 10 to the 6th x to the 1 plus 0.003 dx. What do you think? Does this integral converge or diverge? We're actually not asking what if the integral converges. We're not asking what the value is. Chapter 6.8 part 2 is all about just does the integral converge or not, finite number or infinite number. If the answer is a finite number, we're not going to worry about exactly what it is, although maybe we can get an estimate on it. Well, you could graph this. That's not a bad idea. It looks like basically all the other things we've ever graphed for the horizontal p-test. So we're starting here at 1. This value doesn't really matter. We won't worry about it. So the question is, does this go to 0 fast enough for the overall area under the curve to be finite? And the answer is you can basically never tell by eye just by graphing it. You could not tell the difference between 1 over x to the 0.9 and 1 over x to the 1.1 by eye. Nobody could. And so while graphing it is okay, they pretty much all look like this, and it doesn't really let us know whether the overall integral is finite or infinite. So we'll say we can't tell by eye if f of x is going to 0 fast enough for the integral of f of x to converge. So what can we do? We have a p-test. Can we apply a p-test here? Seems like we might use p equals 3, but so let's say, can we do a horizontal p-test with p equals 3? Well, the p-test only applies to 1 over x to the p without all this other stuff. So we can't directly use the horizontal p-test with p equals 3. But we can think about, so we'll say we can't use this not immediately. But let's think about what we have. 1 over x cubed plus 29x squared plus 10 to the 6th x plus 0.003. How does that compare to 1 over x cubed? Well, you agree for positive x, the number in the denominator here is bigger than the number in the denominator here. So if I'm dividing by a bigger number here, the fraction must be smaller. Notice all these coefficients are positive. So each new term just adds something more to the x cubed, so the denominator here is bigger than the denominator here. So if we were to graph 1 over x cubed, what would it look like? It would always be bigger than my original function. So can we use that knowledge? So that's kind of an upper bound, right? Hasn't some person been talking to you about upper bounds and lower bounds this whole semester? Now we have a curved upper bound. That's kind of interesting. What do we know about the integral 1 over x cubed dx? Does that converge or diverge? The integral converges, since p equals 3 is bigger than 1 by the horizontal p-test. So the area under this blue curve is finite. What does that tell us about the area under the black curve, the original integrand? So the area over 1 over x cubed plus blah, 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 like we have up there. This integrand is less than that. So this converges. So this converges because it's less than that one, and this one converges. So there we did a direct comparison of an integrand whose integral we know converges with some yuckier integrand, but at least we knew it was always smaller. So we call this a direct comparison test. Comparing one integrand and it was smaller than an easier integrand. Whose integral converges. Okay, so if the integral you're interested in is smaller than a convergent integral, then your integral is also convergent. Does it work the other way? Let's think about that. Maybe in the next video.